15 minutes late into lunch, if you don't mind. I thought that was important to finish with Gerst and John.
Wrong talk. That's okay.
She's really talented. She could do that one too.
Oh, I'll see what I can do. Is that your water? Nah. Okay. Good morning. Thank you all for at least staying here. You can sort of snooze a little bit because I'm not going to be nearly as interesting as Gerst and Grunsfeld. I am extremely honored to be here today. As most of you already know, those of you who actually do know me, I'm not really an expert in geology, even though I was invited to speak on lunar geology. And you may wonder why. And in fact, I sort of wondered why. And it's actually more than a little intimidating and also sort of presumptuous for me to speak on lunar geology to this group, since what I have learned about this topic actually comes from listening to the experts who are in the audience. So instead of delving into the scientific details which are being presented by the experts here at this meeting, I'm going to instead talk about the importance of geology in exploration and understanding our solar system. So I'm sort of going to punt a little bit and talk about a fluffier topic than the details that y'all have been so wonderfully discussing all week. Now, got to make sure I know how to work this. Okay. It worked. It worked. Okay, although science and exploration are actually different things, they're complementary. Oh, that's even better. Thank you. I can see now. They do have often a symbiotic relationship, driving each other forward. This is especially true in planetary science, planetary exploration. Exploration is often not solely about science. It can incorporate commerce, finding resources to exploit, political expansion, as well as expanding our knowledge base, any of a number of things. But often science is an integral partner, even if it's not the main focus when it's opportunistic. In planetary science, the science that we do is often very deeply coupled with exploring new worlds. Every time we explore a new world, we learn about it, especially its geology, its physical structure, its substance and composition, processes that act on it, events that shape its structure. Now, human and robotic explorers can be used in complementary manner, taking advantage of their unique natures, roles, and the best use of each of them. Robots are often best used in circumstances where I'll call them the 3 Ds. It's dull, it's dirty, and it's dangerous. For tasks that call for repetitive, high-precision activity with minimal self-determined judgment, or when you can afford to wait for the latency, it makes more sense to use robots than humans. Types of tasks that can and should be tackled by robots include things such as emplacing geophysical networks, performing global mapping, possibly returning samples from a geologically simple terrain. But humans are best used when conditions require judgment, creativity, flexibility, real-time interpretation, decision-making. Humans are better adapted to deal with the unknown. In fact, some problems do require a human presence for interpretation. The big picture, disparate data interactions, you know, all that higher brain function stuff. There are interesting places on the moon, such as Compton-Belkovich as an example, that have sufficiently complex geology that I really believe that they do need to have direct human interaction to work out what that geology is, document it in a usable way, and collect appropriate samples for ground-based laboratory analysis. I generally do not think of robotic exploration as simply precursors to human exploration, but robotic missions are very important as precursors to humans, since the cost and complexities require some characterization of a destination prior to going there. That is, if you wish to keep your human assets alive. There is a limit to that, but it is still important. The key to successful and safe exploration of our solar system will be applying the proper balance between humans and robotic tools. In other words, it's using the right tool for the right task in the right location. Orbiters, landers, rovers, sample analysis, they all have their unique role to play in helping us develop an understanding of the bodies within our solar system. We have studied and continue to study the moon with both direct and indirect access, having experience through orbital and landed human and robotic explorers. We have important orbital, mineralogical, geochemical, geophysical data sets, and coupling these remote sense data with detailed information gained from analysis of samples from Apollo, Luna, and meteorites in laboratories on Earth give us a much better understanding and confidence in the interpretation of the formation of the moon and how it evolved to its present state. Geology can be thought of as the heart of exploration. It's where the story of lunar origin and evolution can be gleaned by providing context, the big picture, the situational awareness necessary for putting disparate data sets together. The reach of the Apollo program in terms is extensive, and it includes both scientific discoveries and developing exploration surface operation know-how. And we build upon both of these as a foundation in understanding and exploring the solar system, especially the inner solar system. Detailed analysis of lunar samples have shaped our understanding of planetary bodies. And because we're, something skipped. Did we go forward awfully fast, didn't we? Well, my slide numbers are different from his slide numbers because it got renumbered when it PDF'd. This will work. The detailed analysis of lunar samples shaped our understanding of planetary bodies. Because we're all familiar with the understanding and the reach of Apollo, I'm going to skip through a bunch of these things. There we go. But basically, the constraints that govern giant impact model come from our understanding of sample analysis, especially oxygen isotopes. Sophisticated models suggest that collision between a large protoplanet and the growing Earth produced rocky, vaporous material around the Earth, and that hypothesis provides us with an explanation of the Earth-Moon system. But additional questions remain associated with how that disk evolved into the moon as we know it, particularly given the existence of volatiles in the lunar mantle. There we go. Short-lived isotope systems help us understand how long after the solar system formed the moon was created, how long it took for crust to form. But the moon represents a nearly complete picture of the processes that have influenced the inner solar system over time. Moon provides us with direct information on the impact flux of the inner solar system. The slope of that impact flux curve, can't talk today, is almost entirely tied to the Apollo samples. Ages of basalts at the Mare sites can be tied to surface flows, with known crater densities providing a calibration to the curve. Must be too fast. The Nice model of solar system evolution was created in part to explain the late heavy bombardment. And of course, recently, you've heard many talks on water content estimates of lunar volcanic glass beads, suggesting that the mantle contains significant water. And at present, it isn't understood to what extent a moon formed from an impact-generated disk can retain water, but it's clearly important that we need to understand the volatile inventory of the moon. In fact, context is important. We already know more about the moon than we do about other planets, in particular from using Apollo and lunar sample collections as ground truth for other data sets. Although we may have samples from other planets brought to us as meteorites, we can't be sure where they came from or how one specimen relates to another. The lunar samples do have field contexts that permit a greater confidence to be put into the interpretation and inferences associated with their analyses. The lunar meteorites are an important complement to the Apollo samples. They come from many more locations on the moon, and so they are likely a better record of crustal composition variability than the more geographically restricted Apollo samples. However, there are many important rock types that are missing for the meteorite collection, and this is likely partially due to the regolith and other poorly consolidated samples that are not coherent enough to survive either being ejected from the lunar surface or entry into the Earth's atmosphere. The lack of geologic context with lunar meteorites causes some of its information to be less than useful. In particular, age data can't currently be tied to geologic formations to help define impact flux. However, there have been analyses of lunar meteorites that attempt to pair the laboratory measurements with remote sensed observations, constraining source region and geologic context of the samples. Although there are still a number of issues that need to be addressed, combined application of diverse remote sensing data and laboratory techniques should at some point enable significant new insights into the geologic context and the potential identity for source regions of these important samples of unexplored areas of the lunar crust. It's definitely a time delay. I mentioned earlier that part of the reach of Apollo went beyond the scientific discovery and included developing exploration and surface operations know-how. To step out of the solar system with humans, there are a few basic capabilities that must be developed. You need to have experience working in a microgravity environment. You need to stay healthy in a harsh radiation environment that's outside the protection of the Van Allen belts. You need to live and work in a reduced gravity environment on a planetary surface, and you need to operate for extended periods of time, long distances from the Earth. The moon can be used to develop mission-enabling technologies and the protocols for wider solar system exploration. In particular, we need to develop discovery-based culture for long-duration deep space exploration and a platform that provides a unique environment with sufficient variability to prepare for those next steps is right next door. Within the human exploration domain, an entire generation has been removed from planetary exploration experience. Planetary surface operations are substantially different from the approach that is used on shuttle and space station. Real-time communication and the simple proximity of Earth with the ability to come home fairly quickly really colors our approach to operations. Low Earth orbit operations are largely procedure-driven. They're highly scripted, large cadre of support personnel, subject matter experts that are available as extended resources to the crew is the mode of operations. The highly scripted operations philosophy is important, and it works very well under certain circumstances, when the missions are relatively short of duration, when they have aggressive goals in terms of science and exploration, and when every second of the mission counts. This implies an ability to have real-time, or at least close to it, communication with members of the crew. It then requires a sufficient number of bright minds available to deal with the problems in a real-time or semi-real-time basis. And that then implies a sufficient amount of money. People are expensive. The final 3 Apollo missions were actually canceled due to operations costs, not hardware costs. Now, although Apollo was largely also used this operations philosophy, there was also a need and an expectation for the crew to conduct some real-time interpretation and decision-making using the observed context at the lunar surface that would not be fully available to the Earth-based support team. This observational discovery aspect of the missions required extensive training for the crew to be able to recognize and interpret their environment. It took about 4 years and over 1,000 hours worth of field and classroom training to develop that capability. Both the crew and support personnel need this kind of training to be able to have effective operations. New astronauts, at least since 2009, have been getting extensive planetary geology training as part of their curriculum, expanding on our Apollo shuttle space station experience, but also using the best practices of current working field geologists. Scripted operations, while probably useful for the early parts of short lunar sortie missions, like the first half of the 7-day expedition, will need to give way to real-time daily work planning to take advantage of discoveries, to be able to adjust your plan as necessary. Space station operations are currently evolving to this method, and in addition, computer technology development and increasing sophistication in intelligent systems will make it possible, to some extent at least, to augment the backroom brain trust and put that information into habitats, EVA suits, rovers, other surface systems that are available to exploration crews. But moving away from these highly scripted operations is crucial to developing the experience base needed for the elevated levels of crew autonomy in long-duration deep space missions. New techniques and improved computer technologies have been used to mitigate some of these issues associated with simulated communication time delays in the latest exploration analog exercises. Much can be learned from thoughtful Earth-based analog exercises in performing engineering tests, in developing operational protocols, and assessing effective and complementary use of human and robotic explorers. Current analog exercises have incorporated real science investigation-based objectives when executing the engineering hardware performance tests. Understanding how to do geology during planetary exploration requires real geologic problems. As you know, but most mission planners and engineers actually don't, geology isn't simply about picking up rocks. It's establishing the overall geologic character of an area so you understand its evolution through time, and that understanding is what informs observations and sampling that supports achieving science objectives. And the whole point is to achieve science objectives. The most recent Desert Rats exercise included integrating mission operations and science operation teams Yep, sure. It's the wrong one. There we go. We've integrated mission operations and science operations teams to work together. This provided some unique opportunities for cross-fertilization that has brought a better understanding of the perspectives and issues related to the two cultures for each other. And although you can play at doing science, if you really want to solve problems and test your hardware, you need an appropriate field setting, you need appropriate science objectives to determine if your hardware and your protocols are actually sufficient to make observations necessary for the discovery. So play acting at science isn't testing science. Our experience from dry runs in rock yards and such shows that while procedures can be learned and practiced, and certain basic aspects of performance of your hardware can be tested, you won't really know if your systems can provide the capability to do real geological sciences unless you actually are out amongst real geologic features. We have successfully incorporated those real geologic questions and objectives to recent field exercises. There we go. Now, not all experience for long-duration deep space missions can be accomplished with Earth-based or low Earth orbit analogs. Although discussions between Earth support and crew on the moon can be near real time, the inability to return home anytime you want provides a much-needed psychological distance to begin preparing for more distant, complicated, and lengthy explorations. The relative proximity is far enough away to experience being truly away from the Earth while still being close enough to incrementally increase your operational complexities. The short light travel time allows direct control of experimental robotic systems such as rovers that will support development of autonomous systems and a better understanding of the effective complementary mix between human and robotic explorers. Using the moon as a stepping stone will assist in developing the techniques and protocols necessary to go further. Specifically, we will learn how to explore by actually doing it. The moon can be a valuable test bed for human adaptation to the space environment. Just as with analog exercises, though, testing hardware in a relevant environment under relative conditions is essential and a valuable way to determine if the systems are capable of meeting the needs of exploration. The moon can be used to perform engineering tests and technology demonstrations of advanced systems for future use. Infrastructure items like power systems and habitats, subsystems that go inside them, instruments to be used, things like drills and analytical instruments can all be tested. And one thing that gets a lot of attention in the human exploration community is in situ resource utilization. And although ISRU is highly specific to the particular body, experience in various civil engineering capabilities can be common and can be usefully applied. And learning those aspects can be very valuable if we want to learn how to live off the land. The moon can also be extremely valuable in preparing for the human exploration of asteroids. There's a lot of debate on what the next destination, NASA human destination should be. And even though we're currently planning for human exploration to a near-Earth asteroid, there's significant interest in the international community to capitalize on recent advances by probes at the moon. In developing capabilities to go to Mars, the order in which you choose to proceed, exploring near-Earth asteroids or going back to the moon, is actually primarily dependent on the order in which the engineering capabilities are able to be developed. Also on potential political and international partnership considerations. So the moon can be thought of and used as a feed forward to asteroid exploration due to many similarities as airless bodies in a harsh, dusty environment. For all that we know about and have learned from the moon, significant questions and opportunities for discovery still remain. A number of well-conducted studies, National Academy, NRC, League studies, have all defined high priority, high level, open questions and objectives for future lunar geological research, but also discoveries from current missions, from new analysis techniques, from new ways of integrating and thinking about different data sets. They all raise new questions to be answered. Lunar geology is at the heart of that lunar exploration program. And even though geology alone does not completely answer all of the desired questions, it is the interface between the human mind and our ability to both ask and answer questions in the lunar surface and interior. It is the context we need to have for the story of lunar evolution as well as the formation and evolution of our solar system. Didn't quite get you back on time.
Oh, that's great, though. Wonderful. Very, very nice talk. Do we have any questions, any discussion that we'd like to have? Wanda.
Hello, my name is Wanda Davis. I'm here at NASA Ames. I am an analog field scientist, and I want to make one observation about the moon that has a bearing on the work that I do, and also my keen desire to have people on Mars. And that would be that the moon represents the closest and the nearest term place that we can go and stay and do work for a period of time. And we will learn how to stay and do work. And probably the first place we will learn to do that will be the moon. Thank you.
Oh, here's one.
All this stuff that leads up to the utilization of lunar resources on a grand scale.
Hold it closer.
Oh, very close. All this leads up to, of course, the utilization of lunar resources on a grand scale. And I'm just curious as to what you would think of how one would go about lifting, say, 350,000 tons a year off the lunar surface.
That's actually a question that I'm going to play a politician here, okay? I'm going to answer the question I wish you would had asked instead of the one you did ask. Because in fact, I don't believe it's credible for us to say that we're going to do that level and scale of activities on another planet in the foreseeable future, frankly. I may be completely wrong, but I don't believe it. I do believe that learning how to do small-scale interesting things is something that we can do and we will do, but I don't believe the moon will be used as an economic force, much like I don't believe that Antarctica is used as an economic force. And but again, this is my belief and my guess at what crystal ball is, that I think that the moon will be used more like Antarctica as the next frontier in research and science rather than economic development.
Okay, and our last question from John.
It's just a quick comment about it's just a quick comment on what you just said. It is really important to make a distinction between Antarctica and other cases, because economic activity is explicitly forbidden in Antarctica. It's by design that it's forbidden. And if it wasn't, there probably would be economic activity down there. So I wouldn't say that because it doesn't happen there, it follows it wouldn't happen elsewhere.
No, I believe that the international community is working its way to developing the protocols and treaties necessary to have the moon in a similar state.
Wait a minute. Wait, I've got to cut you off. I've got one burning question here with John, then we've got to get to our last speaker. It's just not fair, but you guys can continue this conversation later.
Okay, this is a hot issue. Is the moon within the economic sphere? And what do we mean by that? Antarctica is obviously a place of non-profit economic activity. It's you do the faster, better, cheaper. You